Good afternoon, everyone. The October season marks the arrival of the Nobel Prizes. There are 6 days, six prizes, six new faces. They can be old also. After all, if you have come across the Nobel laureates, there have been some people who have won the Nobel Prize twice or thrice. Anyways, but the important thing that I should mention, or all of you know, that this year's Nobel Prize is marred with controversies, is marred with wars. It has been shattered by the Ukrainian invasion. Russia is trying to gain control over it. There is a fallout of the COVID pandemic. There is climate change crisis. Then we have inequality spread all over the world. There are conflicts in Ethiopia, Somalia, what's in Somalia. So if we consider all these, what makes a person worthy of Nobel contention? Now that is according to the selection procedure has been, or whatever the nominations or the candidates that were considered by the jury, that is not available for the period of up to 50 years. So probably we'll be alive by that till that time in order to know what the procedure or what the criteria was in selecting the laureates. So the laureates this year, which have been nominated and who have won the prize, they have joined an elite roster of people from various fields. There are six prizes. So we started with medicine. Then on Tuesday we had physics. Then Wednesday we have chemistry. Then Thursday we have the literature. Then on Friday we had the Nobel Peace Prize, and finally on the coming next Monday we had the prize for economics. So that is, I think you can regard it similar to the UPSC mains timetable, although it's spread over a period of 5 days. But anyways, so getting to the main point, there have been clamor by the people also. For example, many people have said that the Ukrainian president Vladimir Zelensky should have been a contender for the Nobel Prize. But at the same time, the Stockholm International Peace Research Institute, or SIPRI, that has contended that the contenders should actually belong, or they should be those persons not at the time of war, but those persons who are responsible for ending conflicts. And we'll also talk about some notable persons, our very own Bapu, who despite his great contributions towards peace and equality and satyagraha, he was nominated for the Nobel Prize, but he was never awarded one. So that is a major discrepancy which we will be discussing towards the end. And regarding Barack Obama, was also criticized because he didn't stay president long enough to win the Nobel Prize. And when we come to the Nobel Peace Prize, we have our own Kailash Satyarthi, who won the prize some time back. Then we have the youngest Nobel Peace Laureate from Pakistan, that is Malala Yousafzai. And then we have some other important personalities also. We had Nelson Mandela and the likes. But there have been also instances where the Nobel Prize winners have not lived up to the expectations or the values enshrined in the Nobel Statute, or what Alfred Nobel had envisaged. And the most common example or most glaring example would be Myanmar's Aung San Suu Kyi, who won the prize in Nobel Peace Prize in the 1990s when she was under house arrest, and she fought or rebelled against the militarism that was spread. But a decade fast forward, we have seen that she has drastically failed in her leadership qualities, and she has stoked discontent, and she is in some way directly or indirectly responsible for the persecution of the Rohingya Muslim minority. Then a few days back there was an instance where the Vatican City, one of the bishops were there who won the Nobel Prize some years back, but recently it has come to light that some years back he was responsible for child abuses in East Timor in the 1990s. So that has been an admonition to him. And then there have been people like Salman Rushdie, who has been in hiding due to the fatwa or the death threat that was issued in Iran because of his famous novel, The Satanic Verses. And recently, if you have come across the news, if you have been following the updates, he was stabbed on August 12th. So there have been, so this peace prize and literature prize are two categories of Nobel prizes that instigate or provoke a myriad of emotions. Sometimes people think that a particular laureate is deserving, and sometimes the omissions are not easily accepted by the people. They think that it is not justified. So all these criteria, and otherwise if we consider, when we consider the sciences, physics, chemistry, medicine, and economics, they are more or less very complex. We often talk about the financial crisis, we talk about the quantum mechanics, then we talk about the Higgs boson, then we talk about the heredity and evolution. So these are normally out of scope, or the people generally, the general class of citizens, they don't want to intervene or understand the complexities or the intriguing nature of those topics. So basically it all boils down to the peace and the literature prize in literature. But if you think that I am just going to blabber and narrate a list of Nobel laureates of this year or past years by copying and pasting from Britannica, you are gravely mistaken. It ain't going to be so. I'll be discussing some concepts in detail. I'll be providing for your convenience 6 different videos, short videos, discussing each of the Nobel prizes and a little bit of the basics, because some things have really intrigued me. They have made me inclined towards researching or finding out what the concepts actually mean, because everybody can cram they can learn who were the Nobel laureates, but nobody cares to understand what lies behind it. Okay, in the MCQs, you might not be asked to explain quantum mechanics or bio-orthogonal reactions, which were some of the bases on which the Nobel laureates of this year were nominated, and they were bestowed the Nobel Prize. But the sciences are what make us. They create life, they have created the earth, and some basics, not complicated. I'll make it very easy so that each and every one of you can understand. So some basics of the Nobel Prize I would like to discuss. So here you can see that the prizes in medicine, physics, chemistry, literature, and peace were established by a wealthy Swedish industrialist, who in his will, allocated some money for bestowing upon the prize winners. And the irony is that Alfred Nobel, who was the inventor of these prizes, he also was the creator of dynamite. So this is a bit of an irony that one person who is delineating the function of the peace prize, he is also creating this sort of incendiary element. Anyways, so the first awards were handed out in 1901, 5 years after Nobel's death. Then each prize is worth 10 million kroner, that is the currency of Sweden, nearly $900,000, or I've also, some places you can also read around $80,000. That depends upon the exchange rate, and will be handed out with a diploma and gold medal on December 10th. That is the date of Alfred Nobel's death. Now, as we have seen, the 5 prizes had been devised by Alfred Nobel, but we have missed out one, that is the Economics Award. It was not instituted by Alfred Nobel, but it was officially known as the Bank of Sweden Prize, and it was created by the Sweden Central Bank in 1968, much after the death of Alfred Nobel. And between 1901 and 2021, the counter has been running continuously, and 609 times the Nobel Prizes have been awarded. And one important thing to note is that, except for the Nobel Peace Prize, all the other prizes are discussed, or they are distributed by a jury which sits in Sweden. Only the Nobel Peace Prize is the one that is just determined. The laureate or the contender is determined by a committee sitting uh, in Norway. Okay, so there because during Alfred Nobel's time, the Norway and Sweden, they were sort of considered to be in a companionship or a union. So often there is a sort of hostility or animosity between the two regions regarding the nomination or the candidature of the prizes. Then, as I had told, the Nobel statutes prohibit the judges from discussing their deliberations for 50 years. So it's probably going to be a while before we know for sure how judges made their picks. So we talk about the Norway, that is the Peace Prize, and Sweden. Alfred Nobel belonged to this nation, and he instituted the five prizes basically. So thousands of people around the world are eligible to submit nominations. They include university professors, lawmakers, Nobel laureates, and the committee members themselves. So obviously they are nominating if they consider themselves viable candidates, so they can also nominate. Then the Norwegian connection. The Nobel Peace Prize is presented in Norway, while the other awards are handed out in Sweden. So I have mentioned this. That's how Alfred Nobel wanted it. His exact reasons are unclear, but the Sweden and Norway, these two nations were united in a sort of a union or congregation till it was dissolved in 1905. Then what does it take? Scientists often have to wait decades to have their work recognized. Now, this is an interesting conflicting fact. Although Alfred Nobel had envisaged that a person who had done considerable work in the fields of disarmament or peace or medicine or physics, chemistry or literature in the previous 1 year, that person should be considered for the Nobel contendership. But now what the committee, the selectors have done is they take the consideration of only those people who have spent their sweat and blood over the past years to make them stand apart, really stand apart. Because if we take quantum physics, there are regular developments every other day, every other week. So they need to do something distinguishable. They need to do something out of the box, out of this world, to be able to call themselves as viable candidates for the Nobel Prize. Then, so Alfred Nobel's will said that the Nobel Prize should be endowed to those who during the preceding year shall have conferred the greatest benefit to mankind, but otherwise it takes decades for the scientists to prove their worthiness. And of course, the important point is, again, if the scientists are taking so much time and effort, so it needs patience and meditation to finally be worthy of the Nobel Prize. So this is one of the quotes of Alfred Nobel: "The person who shall have done most or the best work for fraternity between nations, for the abolition or reduction of standing armies, and for the holding and promotion of peace congresses." So he intended that this should be some of the criteria for deciding who deserves to be awarded the Nobel Prize. So finally, the first section we come to is Physics Nobel. So these are the names. Of course, I'm not interested in remembering them, although you should have slight idea. So Alan Aspect, John F. Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. So you might have heard about quantum physics or quantum mechanics time and again, but if you just remember this, or if I just reiterate the names and not go into a little bit of detail, then it would not help my cause, at least. But it is definitely my discussion is definitely going to benefit you, because I'm going to explain it in simple terms, and it will get imprinted on your mind. So basically, what is quantum physics? Quantum physics, first of all, it's synonymous with quantum mechanics. We consider this pen, we consider this ball, but if we consider the nib of this pen, then this nib of this pen is comprised of billions of electrons. If we consider this as a small electron, we cannot actually see that electron. So quantum physics basically talks about, it discusses the particles, the subatomic particles, which are normally which are the actual building blocks or the atoms and molecules which finally make up the complexities that inhabit the earth, which include us, the animals, the plants, and various other organisms. So it talks about the minuteness of the matter. The study of matter and energy at the most fundamental level, it aims to uncover the properties and behaviors of the very building blocks of nature. So quantum science may even reveal how everything in the universe or in multiple universes connected to everything else through higher dimensions that our senses cannot comprehend. So when I'm talking about higher dimensions, I'm not talking about Doctor Strange's multiverse, because that is pure fiction, but here quantum physics is very much real and we are making continuous efforts to make it more comprehensible. So the origin of quantum physics, if we consider physics in general or mechanics in general, there are generally two sides to it. One is the Newtonian physics, which is the classical. We know the apple, or we all know the story of the apple falling on his head and his discovering the law of gravity. We know about the formulas, if you remember, gmm upon r square. We know the Newton's three laws of motion. So but that classical physics is applicable only to the large bodies. Large bodies, I mean, I will also include the small organisms like ants and cockroaches, but they are also under the aura of the classical physics. But when we consider electrons, protons, neutrons, the muons, the quarks, all these particles, the motion, their position, their momentum, their existence cannot be explained by classical physics or classical mechanics. For that, we have to understand what is meant by quantum physics. So the field of quantum physics arose in the late 1800s and early 1900s from a series of experimental observation of atoms that didn't make intuitive sense in the context of classical physics, that is basically dealing with the Newtonian physics. Among the basic discoveries was the realization that matter and energy can be thought of as discrete packets or quanta that have a minimum value associated with them. So to explain it in a bit detail, what this text is talking about in simple terms, quanta means discrete packets or discrete values. So for example, I came across an example that if I'm a firefighter, if you have seen foreign shows, I don't know about the firefighters, how they approach the emergencies in India, but if we have seen Australian firefighters or in TV shows or such places, so basically they have a kind of a pole bar. They are usually sitting on the upper floor, and when some emergency strikes, when the alarm rings, so they slide down this pole. So this is a continuous system. For example, so if we consider this pole and we consider this firefighter here and we mark some of the positions 0, 1, 2, 3, 4, 5. So this firefighter, when he slides down that pole, he will encounter all the values, not only the integer values, not only the whole numbers, but all the values, all the real numbers in between. But if I take the same instance of blocks, or if I consider myself or some person, if we consider this apple like it has been given, so if I am picking an apple, so obviously I will not be in a continuous position. If I am climbing the tree or if I am climbing the ladder, there will be certain rings to it. So this discrete places. So first I will be going to 1, then I will be going to 2, then I will be going to 3, or then I will go into 4, and when I come down, I'll not be, just hypothetically, I'll not be traversing or coming across the values in between, unlike the firefighter. So this is the phenomena of quantum mechanics, that is discrete quantities. So this is the basics of quantum mechanics. Then, for example, light of a fixed frequency will deliver energy in quanta called photons. So like we said, that we can consider quanta as discrete packets of energy. Okay. So even light, when we measure the energy, the important point to note in quantum physics is that the small particles which are being studied in quantum mechanics or quantum physics, like electrons or the light particles, they both have the matter properties as well as the wave properties. In classical physics, we normally deal with the matter or the mass. We calculate position and momentum, but here both the aspects need to be considered. That is what is known as the particle wave duality, the dual nature of a particle which is studied under the quantum mechanics. Then each photon at this frequency will have the same amount of energy, and this energy can be broken down into smaller units. So there is a fixed, when we talk about light, there is some fixed wavelength with it, some fixed frequency in it. And if you remember the value of energy, we have energy is equal to h mu. H is a constant and mu is the frequency. So, or we can say hc by lambda, where c is the c is the speed of light and lambda is the frequency of light. So these are discrete units. Then in fact, the word quantum has Latin roots and means how much. Okay, so conceptualizing, building upon what we have discussed in the initial parts, the knowledge of quantum principles transformed our conceptualization of the atom, which consists of nucleus surrounded by electrons. Often we have studied in school also that we have, for what we say, that we have a nucleus in consisting of protons and neutrons, and around that we have orbits in which the electrons spin or rotate. But actually it's not the case. The electrons, we cannot determine the exact rotation. It's not the electrons rotating. Actually, the electrons are distributed. They have a probability distribution factor. So if there is a probability, for example, this nucleus is surrounded by a probable space in which there is a probability, or the probability or the hope that an electron will be found, or the there is a probability that the electron will be found. Then early models depicted electrons as particles that orbited the nucleus, much like the way satellites orbit the Earth. That is not the case. We always have a probability or a chance. I was not getting that word. Chance that an electron might be found in that cloud. Then modern quantum physics instead understands electrons as being distributed within orbitals. Mathematical descriptions that represent the probability of electrons' existence in more than one location within a given range and time. So you might be seeing this wave structure. So unlike what we have been taught generally in school, which was based on the Bohr's model. Niels Bohr was the scientist who pioneered this model, in which he said that electrons are revolving. So this is now outdated. We now know that there are something terms known as orbitals. These are different from the orbits. These orbitals are the spaces, the functions where this is a distributed phase dependent upon the amplitude and the wavelength of a particular wave, and it determines the probability in which the electron can be found. Then electrons can jump from one orbital to another as they gain or lose energy, but they cannot be found between orbitals. So that is what, because we talked that the basic fundamental of quanta was discrete particles. So when we say that suppose there is a sort of an orbital or place where an electron is there, we don't know, there is a probability of electron. When it is of a higher energy and this orbital has a lower energy, so when it will go down to the lower level, obviously some energy has to be emitted. So that energy, when we discuss that energy will be associated with some sort of wavelength, and that when the electron jumps to a lower level, that gives rise to what we known as an atomic spectrum. We know that the rainbow Vibgyor, but that is actually the difference in the wavelengths. When the electrons from the light, they jump to different levels, so the energy which they emit, if the wavelength of that energy corresponding to that energy confers or coincides to a wavelength of a particular color of visible spectrum specifically, then it will show a color. For example, it can be blue, it can be red, it can be yellow. I'm not describing or going in depth into the order, but we can say that red is the out of Vibgyor. We can say red is the color, red is the spectrum which the highest wavelength and the lowest frequency. So obviously the color red will have the lowest energy because it has the highest wavelength, and the blue color will have the lowest wavelength among Vibgyor and the lowest wavelength and highest frequency. So no need to go into that. So we have discussed the basics of what the quantum mechanics feels like. So moving on, so we had talked about this wave particle duality. So when we talk about any particle which is being studied under quantum physics or quantum mechanics, it has both wave characteristics and the particle characteristics. So I've just mentioned kind of this diagram. So it has a wave function also, and this has a particle function also. And you might have come across this term photoelectric effect, which is the principal method by which solar energy is utilized to produce current or to it is behind principal function of producing solar energy. And it is also when light is striking here, so what is happening is that these electrons in that particular material, for example, we use semiconductors generally, which is silicon or germanium. So when these light particles, they are giving off their energy to these electrons. So these electrons, after getting excited or gaining energy, they seem to jump off there from this material, and in turn this light energy is converted into the electrical energy in the quantized form. So these packets of energy are coming in the quantized form, and these are providing the energy for these electrons to jump to the higher or lower levels. Then the principle dates back to the earliest days of quantum science. It describes the outcomes of experiments that showed that light and matter had the properties of particles and waves depending on how they were measured. Today we understand that these different forms of energy are actually neither particle nor wave. They are distinct quantum objects that we cannot easily conceptualize. So going here, one of the main principles of quantum mechanics is superposition. Here actually I had inserted a GIF. So actually what it tries to say is that when we study about any quantum particle like an electron, its position and velocity or momentum cannot be determined at the same time. So for example, there is a skateboarder. There is a skateboarder who is going from one place to another. So without the observation, without observing, we cannot say that at which position the skateboarder will be. He can be at 0 position also, or it can be at first position also. Similar is the function, similar is the way in which the quantum particles under the influence of quantum mechanics behave. So an electron or any subatomic particle, it cannot be determined at a particular position, cannot be determined. It is only through observation that one can determine one thing or the other. So there is also always a conflict that whether we are measuring the subatomic particle in its wave form or its particle form. We'll understand more about it. So this is a term used to describe an object as a combination of multiple possible states. It can be in 0, it can be in 1. A superposed object is analogous to a ripple on the surface of a pond, that is a combination of two waves overlapping. In mathematical sense, an object in superposition can be represented by an equation that has more than one solution or outcome. So if you have solved any linear equations or quadratic equations in maths up to 10th class, or in maybe in non-medical also, so sometimes what happens is some equations, when we find out the value of x or y variables, more than one solutions come, and particular wave equation which is used in quantum mechanics, that is referred to as the Schrodinger's equation, which gives the multiple positions or multiple solutions, and which in turn define what we have been talking about since the beginning, that is the probability distribution, not the exact position of any quantum particle. Then uncertainty principle, there was a scientist known as Heisenberg who gave this principle similar to a dice. We have been talking about probability. So in simple terms, if you cannot understand the graph, I have a So for example, we have been talking about the wave function. So till now in the school level, what we were discussing, okay, electron, there is a nucleus, there is a proton, there is a neutron, and the electrons are being observed as particle. But according to quantum mechanics, it has waveform, it has a dual nature. So it should be considered as a wave function. So if we describe the electron space, the probability distribution of electron, so it will be something, if I consider this an axis and if I consider this a wave. So if there is a quantum wave like this, so these crests and these bottoms, they indicate the probability of finding an electron. The probability space of finding the electron will be this. The electron can be found somewhere here. It can be found somewhere here in this space. But this crests and troughs, this is the position where the probability of finding an electron will be maximum, and this is the position where the probability of finding an electron will be minimum, because it is being considered in the form of a wave. Now what happens is, in the previous slide we had talked about the superposition. So what happens is, if we want to find out the actual probability distribution of this particular quantum wave, we have to square the function of that wave. We have to multiply equation, for example, in simple terms, a square x square plus y square plus z square, and we have to amplify it. This is basically which is declared, that is the amplitude, and this is the wavelength. Now you can see, normally wavelength, if we consider a proper sine wave with uniform crests and troughs, here the wavelength is definite, but in this case the wavelength is varying, because the distance between the two crests or the two troughs might not be the same. So the point is, in order to find the momentum and position of that particular electron in this probable space, we square that, square this function. So this will be repeated. So what happens is, this will be there. So this will become twice of that. So the important point what this wants to say is that what happens if we consider a quantum particle as a sine wave, then we know for sure that its wavelength will be constant. But if we have to determine the position of that electron, then we have multiple probabilities. That is, according to what I have explained there, the electron can be here, electron can be here, electron can be here. So although the wavelength is there, and wavelength determines the momentum of that electron, so that quantum particle, if we know the wavelength, we are uncertain about the position. So that is duality, or that is the problem, that measurement of quantum particle cannot be made accurately. But again, if we find out that the wave function for a particular probability distribution of an electron is a simple one, for example, if we take just this wave, this kind of wave with no other, so we know that here the amplitude, this amplitude is the amplitude which determines the probability or the position of electron. Here the electron probability can be easily determined, but now we don't know the wavelength, because the crust, when we superimpose two or more waves, two or more electron waves, then this wavelength becomes variable. So in simplified terms, if you are unable to comprehend this, in quantum physics, the main problem that arises is that we cannot measure the same the momentum and the position of the particle at the same time. Either we know the position and not the momentum, or we know that the momentum and not the position, or there is a general confusion, or there is general decoherence. The term is decoherence, for example, which we discussed in the terms of that skateboarder. He can be anywhere in between the position 0 and 1. So this is known as the Heisenberg's uncertainty principle. Here, just for fun purposes, if you have come across this TV show on Netflix, Breaking Bad, so this actually is not the same person who gave the principle, but this is another person. He's a protagonist of Breaking Bad. He was a chemistry teacher, so he also had an alias known as Heisenberg. So just for fun purposes, and so moving on, just to explain to summarize, what is the uncertainty principle? Mathematical concept that represents a trade-off between complementary points of view. In physics, this means that two properties of an object, such as its position and velocity, velocity corresponds to velocity will correspond to its wavelength, and cannot both be precisely known at the same time. If we precisely measure the position of an electron, for example, we will be limited in how precisely we can know its speed. So this is what is meant by the duality principle, similar to, in simple terms, in dice. Even if I flip a coin, if I take a coin, I'll not take out my purse this time. So we have two positions, heads and tails. So as long as the coin is in the air, we don't know whether whether it is in the heads position or the tails position. It is in a system, it is in a space of decoherence, or it is in a space of constant constant confusion, or constant different types of probabilities. It is only when it lands on the surface, then only we can say that it's heads or tails. But this cannot be extrapolated because this is just a simplified concept. The coin is actually not part of the quantum physics. So this is what is there. So now slowly and gradually we are approaching towards what the Nobel laureates in physics actually worked upon: quantum entanglement. So initially, previously in the one of the previous slides, if you remember, we had considered the probability distribution of electrons as similar to the ripple effect. For example, what is happening is, if there is a pond, so if there is a pond and I throw a stone in it, so some ripples will be created, these waves will be created. Then one of my friends wants to disturb this wave, this sine wave, proper wave. He also throws another pebble, then its ripple will again. So when these waves will combine, then there will be a resultant wave which will be sort of sum, or it will be a coupling of both the waves. It will become represent a single system. So similar to that, we can talk about the electron waves also. For example, if we have a wave going like this, we have so if we have a wave going like this, and then we have a wave, another wave. So when these waves, these quantum waves or electron waves, they come into contact with each other, they are superimposed with each other. So the resultant might be, not exactly I'm going, the resultant might be something like this. So this is one of the basic principles of quantum entanglement. Now what it means is that even if after superimposition one electron, these are this is one electron 1 and this is electron 2, after combining or juxtaposing with each other, that is when they come into contact with each other, their wave functions come in contact, so this superimposed wave function is formed. Now, for example, these electrons are continuously moving quantum particles. So if we take this electron, for example, if we place this electron 1 on a physics lab on Earth and one electron I take it to Saturn. So the principle of quantum entanglement says that if we observe this electron 1, and then if we know this property, then we can be able to know definitely the property of this also. So in a way they are entangled with each other. Now an easy example for this is, for example, I'm driving and I suddenly feel the urge to, my stomach is gurgling and I want to eat something. So I go to a fast food shop. I tell him that I want a burger and I want a hot dog also. I'm using American jargon because that is what the case is in literature online. So what he does is he does not directly give it in a wrapper like what we have in India. So he packs them in 2 boxes. So now in one box there will be a burger and in one box there will be a hot dog. But when as long as I don't open any of the boxes, I cannot know for sure which box has the burger and which box has the hot dog. So this is similar to the uncertainty principle which we have discussed, the Heisenberg uncertainty principle. But so this is the waveform of that electron or quantum particle. But as soon as I open one box and I see that it contains the burger, then without opening this box, unless and until there is some receipt issued by that vendor, so there is definitely going to be a hot dog in this box. So this is simplified. So in a way these are entangled to each other. If we know the property or we know what's in one box, we can know what's in this other box. Similar concept can be applied to quantum entanglement. Now another concept, if you don't understand, just listen to it, keep an open mind. If you have studied chemistry to 11th or 12th, you might have heard about quantum numbers like n, l, m, yeah, 2, like this. So n is the principal quantum number. Then this is, I'm forgetting the name of this quantum number. This is the magnetic quantum number, this angular momentum quantum number, the magnetic quantum number, and the spin quantum number. So for the time being, for the under the scope of quantum mechanics, we'll consider this spin quantum number. You might have heard that electron has a spin. So normally if I consider this as an electron, so normally what we understand by a spin is the electron is either has a positive spin, it is rotating like this, or it might have a negative spin. But that is not exactly the case. Why? Because it's a subatomic particle, it is continuously in a state of sort of flux, and it will not exactly be spinning, it will be in a probabilistic distribution of some spin in between, which we cannot determine. But again, applying this concept of quantum entanglement to 2 electrons, if we consider these 2 electrons, if they come into contact or entanglement with one another, they get superimposed, their wave functions get superimposed. So if one electron I keep on Earth and the other electron I keep on Saturn, then if I observe the spin, if I observe that here the spin is positive, If I observe that the spin here is positive, then I will immediately come to know that the spin here will be negative. So this is what is known as quantum entanglement, and one of the chief concepts which the Nobel laureates of this year worked upon. Now, what Einstein had to say, he disapproved this, because according to the theory of relativity, these two electrons are separated by light years, billions of light years. So it is not possible that if we measure the properties of one electron, then the other property can be known. That is, the entanglement cannot be justified, because for that the particle, the speed has to be greater than light, which will violate Einstein's theory of relativity. But what one scientist came into picture, this feature which perturbed or which worried Einstein, this was known as spooky physics, because obviously it is in scientific terms, spooky is different for the general class of citizens, but for Einstein, what this phenomena, this quantum entanglement, was impossible because it was not allowed by the theory of relativity. So this one person came, Bell, who gave a concept of Bell's inequality. Now we will not go into the detail of this, because the interesting part is more or less over the quantum mechanics. So based on quantum mechanics, and in order to prove the quantum entanglement, in order to get rid of this spookiness which was pervaded by Einstein, he said that there are some hidden variables inside this quantum particle which can be used to establish correlation between the two electrons which are spaced very far apart, and this can easily justify the quantum entanglement. Now what limitation the Bell's inequality said, that the variables may be such, the hidden variables may be such that the full scope, there may not always be a correlation between two or more quantum particles. But the current Nobel laureates, the physics Nobel laureates, they disproved Bell's inequality and said that there are always variables, there are always such features or conditions by which a multiple number of correlations can be found. So this is the basic premise of the work done by the physics Nobel laureates. We don't need to go into the detail. The interesting part is quantum physics. Now we'll come to why this research has been considered important and worth the recommendation for the Nobel Prize. Just one other concept of quantum mechanics is the Schrodinger's cat. It is similar to there was this person Schrodinger who did this cat experiment. Now it is similar to what I discussed with the burger and hot dog. So what he did, it is a sort of hypothetical experiment. I don't think he really took a cat and placed it in a box. So again, as before, so there is a box, and there is a cat. So what he did was he placed the cat in the box, then he placed a radioactive substance here, he placed a Geiger counter here, and he placed a poisonous chemical here. So what the premise was, in that box, when this radioactive material decayed, so after a certain point of time, this will trigger the Geiger counter, which in turn will let the release of this poisonous gas or poisonous chemical, and this will lead to the death of the cat. But unless and until we peer or see inside that box, we cannot say that whether the cat is alive or whether the cat is dead. So this, again, the duality or the wave particle duality, it's constantly in a state of flux, similar with the quantum particles. So all these quantum entanglement, the probability distribution, Schrodinger's equation, the Heisenberg uncertainty principle, they are more or less linked with each other, and together they form the foundation or the building blocks of what is known as quantum mechanics. So some explanation, because many of the concepts of quantum physics are difficult, if not impossible, for us to visualize. Mathematics is essential to the field that gave rise to the wave function and Schrodinger's equation. Equations are used to describe or help predict quantum objects and phenomena in ways that are more exact than what our imaginations. And again, to repeat, we are not talking about Dr. Strange's multiverse. It's besides that, beyond that. For example, the position of electron may not be known exactly. Instead, it may be described as being in a range of possible locations, which we described in terms of the probability distribution function of wave, such as within an orbital, not an orbit, with each location associated with the probability of finding the electron there. So this is what Schrodinger's equation looks like. Pretty scary, but this can be, like I said, that the electromagnetic waves, they follow this kind of wave function. They sort in the feature, again, if I share a physics concept with you, the electromagnetic waves are such that the wave propagation is perpendicular to the motion of the particles. So that is, and if we distinguish them from the sound waves, the sound waves, the wave propagation takes place by contraction and expansion. So the movement is parallel to the wave propagation. In this case, if the wave propagation in this direction, if the wave is propagating in this direction, then the motion of the particles is in this direction. So basically, this is how the sound propagates. If I place my ear to a sound coming, so this contraction and expansion will lead to the propagation of the sound wave towards my ear. But when we talk about light wave or any other such electromagnetic wave like an X-ray, so it follows this electromagnetic shape. Then, given their probabilistic nature, quantum objects are often described using mathematical wave functions, which are solutions to what is known as the Schrodinger's equations. Waves in water can be characterized by the changing height of the water as the waves move past a set point, just as a ripple in a pond or note played on a trumpet are spread out and not confined to one location. Quantum objects can also be in multiple places and take on different states, as in the case of superposition at once. So I think it is now vividly clear, if not entirely clear. Many concepts are now clear to you. One other concept that came to my mind, which I just wish to discuss with you. First, let us. So this is again observation of quantum objects. This is just an extrapolation or explanation in detail of the wave nature of the duality of the quantum particle, that is the wave particle duality. So what we have been talking about the decoherence. So early in the field, scientists were baffled to find out simply observing an experiment influence the outcome. So we'll discuss a famous experiment known as the double slit experiment. For example, an electron acted like a wave when not observed, but the act of observing it caused the wave to collapse and the electron to behave instead like a particle. So it's like saying in simple terms, what this literally means is that as long as we are not observing the electron, the electron is behaving like a wave, and when we observe the electron, then it behaves like a particle. This was a GIF, so we are it is not showing the other side, but when we are observing it, the electron is becoming a particle. But that observation is just mere, that is an illusion, or that is some sort of vagaries of the conscience, but exactly it is not so. So it is misleading, in the term observation is misleading in this context, suggesting that consciousness is involved. Instead, Measurement better describes the effect in which a change in outcome may be caused by the interaction between quantum phenomena and the external environment, including the device used to. So there are multiple various factors involved which influence the outcome or the nature in which a quantum particle such as an electron is behaving. So this is we have talked about the waves. So how we are observing the quantum waves. So this was the double slit experiment. I'll just draw a simpler diagram first. So what is happening is the experiment. If for example I take a paintball gun, if you have seen, and I place three boards here to create two slits, and I have a screen at the rear. So this is like we have the gun, the paintball gun, and we have the three boards where two slits are there, two spaces are there, and then we have the screen on which the impression of that paint will be located. So when I fire this paintball gun on all this uniformly on this, then obviously the paint that will go through these gaps, it will appear like this. But when I use an electron gun or something that is used to project electrons on the screen with the same arrangement, the pattern will not be like this. It will be observed that the majority of the electrons strike here, then it gradually diminishes in the form of waves, and there are gaps in between which do not correspond to the gaps which are physically present here. So in a way, now this, if we consider the diagram which I have given, so this is a monochromatic light source. This is a single slit, so light is passing without any. Now what is happening is the wave is getting divided into two parts. One electron wave, just like ripples in the water, due to one stone or one phase of light, it is contributing to this wave. Other source is contributing to this wave, and there is a superposition of the waves like we have discussed. So the maximum amount which you can see is at the center, just behind this. Ordinarily, if we observe, if there was a paintball gun which we used, the impression will not come here. But when we observe the electron wave, so it is the majority will be here, then it will diminish towards the outer side. So this is an example of term in physics known as diffraction or interference. Then shooting particles such as photons or electrons to a barrier was originally used in 1801 to show that light is made up of waves. To further proof, this is an experiment to prove the observation that it has dual nature, that is both particle and waves. And since then, numerous incarnations of the experiment have been used to demonstrate that matter can also behave like a wave, and to demonstrate the principles of superposition, entanglement, and the observer effect. So we have comprehensively, without I think going into much detail, we have understood quantum mechanics. Now, work of the Nobel laureates. So I have discussed in detail. You can just read the text. Just pause the video and read the text of what it is, mostly theoretical. So what they did, it is mentioned about the Bell's inequality and how they violated it, and the important point is the application of quantum mechanics. One can say that if we don't know quantum mechanics, we are not able to work or function a nuclear power plant. Then we have qubits, we have the quantum cryptography, then we have technologies like quantum computers which can perform complex calculations within a fraction of a second. And even if I tell you an example, in I think Switzerland, like in here we have electronic voting machines, and we have also introduced the voter verified paper audit trail, VVPAT, but still there are always claims after an election that it has been mismanaged and it has been vandalized, and votes have been put here and there. But in that case, what they have done is similar voting machine, but they have used quantum entanglement or quantum physics to ensure the authenticity or genuineness of that particular election. So since we have talked about the quantum entanglement, in simple terms, if any person wishes, if any person wants to change the outcome of a particular vote or result, the other entangled position, the other entangled information will also be affected, and in turn the cryptography, the quantum cryptography will not allow that counterfeit to take place. Some of the important this is the example of the spooky entanglement which was clarified by Bell. Then this is the significance of quantum mechanics. Again, quantum research, quantum computers, even quantum money. We had talked about bitcoins, but there is quantum money also. Then quantum cryptography, I've given an example. Even quantum teleportation. But teleportation here, I'm not talking about X-Men's Nightcrawler. It does not work like that. I cannot teleport the material nature. It's going to be a wave form. It is quantum mechanics will help the teleportation of the information contained in the quantum particles, not the whole human. Then we have qubit technology, we'll not discuss. So quantum technology is manifested through applications in secure communication, disaster management, and all this simulation chemistry. So it has a multitude of applications, and in Australia I was just reading a study that by 2040 the quantum industry will be equivalent to a massive $4 billion industry, and it has a potential to generate a lot of jobs. So we might look into that in the future. So this concludes the physics part of the Nobel Prize. I know it was a bit exhaustive but informative as well. So in the next video, we'll move on to the chemistry Nobel Prize.